This lecture will be on nuclear energy for AP Environmental Science. So there's a lot to unpack here with nuclear energy, and for that reason, this is going to be one of the longer videos, if not the longest. It's going to be the longest for this unit. So we're going to be talking about the same enduring understanding where we're looking at the different energy sources. We're going to be looking at how we generate power with nuclear energy and then the environmental effects of that. But like I said, a lot to unpack. And with that comes a little bit more vocab than our other energy sources, so you can pause this and write this down if you need to. So we'll start with how we generate power with nuclear energy. The way that we get power is we have to start with nuclear fission. And that is where a parent isotope that is unstable or fissile or radioactive is going to split or undergo fission, break apart into two daughter nuclei, as well as some neutrons that are going to be made. This is going to release a lot of energy. And if you have not atoms, but pounds, tons of this material, it's going to release enough energy to power a power plant. These neutrons are going to come out with extreme force and they're going to strike other radioactive isotopes, other parent isotopes, and they're going to break those apart. Most of the time when we're doing this, we're going to be using uranium, and you guys might hear of like a chain reaction in a nuclear power plant. This is what we're talking about, where this one uranium atom gets struck with a neutron, goes on to break apart into two daughter nuclei, which can be radioactive in themselves and are. And then this neutron comes back and strikes um, another uranium atom, and then another one, and then another one, and another one, and a chain reaction. Because we have to mine uranium, it's a finite resource. We're going to say that nuclear power is a non-renewable energy resource. It is cleaner than some of the other energy sources. Notably, it does not produce any gaseous emissions. There is no waste gases coming off of a nuclear power plant. No carbon dioxide, no methane, no nitrous oxides, no sulfur dioxide, no waste gases. So nothing goes into the atmosphere except for steam, which we will talk about a little bit later. Before we get too into it, I'm going to mention that we're going to be talking about two types of reactors. You do not need to know these types, but when we talk about electricity generation, these are the types of reactors that we're going to be talking about: pressurized water reactor and boiling water reactor. But again, you don't need to know the names. You'll just have to be able to describe the process of electricity generation through them. There are other reactors that are going to work in more or less the same way that we're going to talk about from here on out, but with some differences that we don't need to get into. And some of those reactors are going to use different types of fuel. So some of these reactors, like breeder reactors, can use spent nuclear waste, old fuel rods that are decommissioned from a normal power plant. In their reactor, but they're still going to be basically working on the same principle. The ones that are doing propulsion of ships, like military ships, like submarines and aircraft carriers, those are going to be doing a slightly different process, but we don't need to go into that or all the complexities there. So in general, we're going to be talking about a pressurized water reactor or a boiling water reactor. And in those reactors, there is going to be a core. And this is what you guys do need to know. So there's going to be the reactor core. That reactor core is going to contain fuel rods, and those fuel rods are literally rods. You saw a picture of them on the last slide, but they're literally rods that are made of pellets of your nuclear fuel. For our purposes, we're going to say that it's uranium-235, but other reactor types may use other different types of fuel. And then there's going to be another type of rods in those reactors, which is actually what you saw on the last slide. You guys saw control rods, not fuel rods. Sorry, my mistake. But those are control rods, and those are in order to capture the excess neutrons. We don't want this chain reaction going and accelerating, going faster and faster and faster and accelerating. And that would give us a runaway nuclear reaction, which you guys may have heard of as something that can lead to disasters, which we will talk about. So we want to absorb some of those neutrons so it doesn't become out of control. So we're going to insert the control rods a little bit deeper into the fuel rod area, in which case it's going to slow down the reaction more because it's going to absorb more rogue neutrons. Or we can pull them out and accelerate the nuclear reaction. Okay, so we can control how much heat and therefore how much electricity we're producing by using these control rods. If they go in, the reaction goes slower. If they come out, the reaction is going to be faster. There's going to be a heat exchanger or a boiler. This is going to be where water is going to be evaporated and turned into steam, and then that's going to move across many tubes at a high pressure and turn a turbine and then power a generator, just like we've talked about with a coal burning power plant, a diesel burning power plant, any of our power plants where we have heat being generated. So after the nuclear reaction process, it's more or less the same in terms of electricity generation. There's going to be a containment structure. You guys will see some pictures of nuclear power plants. I'll point out the containment structure. And that is like meters thick concrete that's designed to contain an explosion inside of the nuclear core. So if there is an accident in the reactor core, they're going to contain that accident, or at least that's the general idea or the goal. The turbines, that spins the generator, that makes the electricity. We've talked about those several times. And then we're going to have cooling towers and cooling ponds, which are going to cool the water before it gets recycled or released into the natural environment. So what does this look like? Over on the top right, you can see a picture where you can see the containment buildings, which have all of the reactor cores in them, and then the cooling ponds, electricity generation down here, all of that stuff. But in general, on the diagram, sorry about the bell, on the diagram, inside of this containment structure, we have the reactor, or the reactor core, and that is going to contain the fuel rods down there, which is red in this diagram, the control rods being black in this diagram, and then we're going to have in this kind of purpley area, the water that is being pumped through to cool this reaction, because there's also going to be water cooling this reaction by circulating around the outside and just keeping everything a little bit colder than it otherwise would. And then that water is going to be going through this boiler, and it's going to be heating up this water that's in the steam generator. Sorry, that was really messy. The water that's in the steam generator, that's going to go at high pressure through those pipes very fast, past a turbine, which is going to spin the wheel of that, or spin the blades of that turbine, which is going to allow that to power a generator, which is going to make your electricity. This water gets condensed, so it gets cooled down and turned back into a liquid, where it is then pumped to these cooling towers, where it will cool off, and then back into the system. You can also have cooling ponds. Those are going to cool off the water. You can release that water back into the river or into the ocean or into the lake. You'll see that a lot of nuclear power plants are right next to a water source because they do need a lot of water. But a lot of that water can be recycled internally in the plant. So once you draw out some water from the natural system, you can reuse that water over and over again. You do notice that off of this cooling tower, there is steam being produced. Again, water vapor, steam, is the only atmospheric waste product of a nuclear power plant. So in brief, in the reactor, you have fuel rods. The reaction speed is controlled by the control rods. Those are going to slow down or speed up the reaction. The fuel rods are going to be used to boil water because of the intense heat that's generated through nuclear fission. So boil water, create steam, steam turns a turbine, turbine powers a generator, generator generates electricity. And then the water's cooled off for reuse. So what type of uranium do we need? Well, we need uranium-235 for this. So most of the time you're going to see the isotope 235 for nuclear fuel. This is a very small proportion of the Earth's uranium, only about 0.7%, but it is what we want. It's the uranium that's fissile, meaning that it can split apart into its daughter elements. Most of the uranium around the world, though, is U-238, which is much less fissile. It's more stable. It does not react as well. So we need to enrich the uranium. We don't need to go into the process of how they do it, but basically they do it by separating it out with density, centrifugation, and we're going to increase the concentration of U-235 to make it not the natural, but the low enriched uranium for reactors, so fuel grade or reactor grade uranium, and it's only going to be like 3 to 5% U-235. The pie chart is greatly exaggerated. We don't want to go further than that because then you can continue doing this process and create nuclear weapons, but that's not what we're interested in. We're interested in clean electricity. So, what are some of the benefits of nuclear? Well, uranium is relatively plentiful. Yes, we do have to mine it. Yes, that does create its own environmental problems, but it is relatively plenty. There's more uranium on the planet right now in terms of electricity production than there is coal or there is oil or natural gas. We have about 200 years worth rather than less than 100 years of those fossil fuels at current rates of use. However, if there was widespread adoption of breeder reactors and molten salt reactors, which can use spent fuel as their, or nuclear waste as their fuel, there's actually about 30,000 years worth of fuel at our current rates. If we bump up those current rates, obviously that will draw down the number of years that we have available though. It does produce no atmospheric pollutants. Again, whenever you see a picture of those cooling towers, it's just steam. Um, there is going to be a little bit of CO2 generated from all of this concrete, but I would argue that if you have a coal burning power plant, you're going to be creating cooling towers anyway. So I would say that the CO2 from construction is negligible compared to the amount of CO2 that you save by using nuclear over the long run. And it is a very consistent energy source. You can even regulate the speed of that reaction so that it goes faster or slower based off of the electricity demands. So nuclear is actually really good to pair with some of our variable energy resources like wind or solar, because in the case of solar, at night, you can run off the nuclear power station and then slow it way down during the day when the solar panels kick on, and then bring it back up at night. But just like everything, there are drawbacks. The first one is thermal pollution. We're going to talk about this on another day, so don't worry about it for right now. But what this is basically saying is that the power plant can just emit really hot water straight into the local environment, the river, the creek, the lake, or the ocean. So you could just release hot water into the environment. This uranium does have to be mined, so there are environmental consequences of that we talked about when we talked about mining. There's a lot of concrete that's used, especially to make the containment structure and the cooling towers. But again, that's a one-time investment rather than emitting CO2 continually through the life of the power plant as you would if you were using fossil fuels. You do produce nuclear waste. Now, this is the huge one. Nuclear waste, as well as it can be dangerous, but like the power plant itself, but nuclear waste is the big one. But there's the potential for disasters, terrorist attacks, military targets, like we saw in Ukraine with nuclear power plants, including Chernobyl, being used as bargaining chips with the two sides, and then the public perception of nuclear as well. So, since nuclear waste is one of the biggest drawbacks, both in terms of human health and environment, let's look at nuclear waste. So, all of the products, until you get down here to something that is stable like lead, of this nuclear series are going to be reactive. Each one of them has their own half-lives. So half-lives are going to vary from anywhere from billions of years. In the case of U-238, the half-life is 4.5 billion years, which is the amount of time that the Earth has existed. So half of the uranium that was on the original Earth 4.5 billion years ago is still here today, the U-238. Some of them are just a few minutes. This protactinium is only 1.17 minutes. Some of them are going to be seconds. Some of them are going to be even nanoseconds. So you don't need to know any of this. You don't need to know the radioactive series, but you do need to know that those half-lives can vary considerably. And you do need to know what radioactivity is. This is the release of high energy particles, whether those are alpha, beta, or gamma, we don't really need to talk about, but high energy particles from the decay of these elements, of when they turn from one to another. And these fuel rods, because they contain an assortment of radioactive products, they have to be disposed of after their functional use. So the fuel rods are nuclear waste. Any personal protective equipment like gloves, suits, those are nuclear waste. Anything that really comes into contact with these isotopes are radioactive waste. So we generate a lot of radioactive waste. Okay. And we do need to dispose of that nuclear or radioactive waste as well. Now, there are 5 basic methods. The first one is on site at a power station. You're going to have a big pool, and in that pool or in that containment pond, which is the term that you should know rather than pool, you're just going to stack all this radioactive waste and wait for it to cool down. This is especially going to be used for high level waste right at the power plant. The control rods right after they come out of the containment structure are going to go into these because you need to let them cool on site for quite a while before you can transport them anywhere. So they're just going to cool them underwater, and water is really good at absorbing and dissipating radiation at a very slow rate that is not harmful at all. You can bury this stuff in a landfill. So low-level waste like personal protective equipment, tools that you use can be sealed in steel drums. That drum can be lined with concrete and then just disposed of in a landfill. Typically, what you're going to do is have alternating layers of clay around this or even concrete around these things in your landfill so that they're never accessible. You can bury them deeper. So medium to high level waste, once it's cooled on site at the power plant, will then be transported deep underground, like an old abandoned mine that is structurally sound. They'll put it in, and then they'll flood the entire area with concrete, so it's essentially sealed in this concrete tomb underground. The best way to do it, which I have here with a triangle. Sorry, that is a star. I'm an idiot. I just was looking at 5 triangles, and in my mind I saw a triangle. Um, yeah, a star. What I have here with the stars is the best ways to go about doing this. The Deep Geological Repository is a facility that is specifically built to dispose of nuclear waste. We'll see a picture of one, and we'll talk about another on some other slides. But you just specifically design it so that for nuclear waste, you have all the safety protocols, all the ventilation, all the you know giant locks on the giant doors, essentially, so that nobody gets in there that shouldn't be. And that's better than an old mine because an old mine was not designed for nuclear waste. This is designed for nuclear waste. People have proposed that you send the nuclear waste to space. That is a really bad idea because you would need tens of thousands of missions, and each one of those has the possibility of the rockets exploding in the air and raining nuclear waste down on everyone. So we haven't done it, thankfully, but people have proposed it. I think it's a horrible idea. Or you can recycle this waste. Now that is like the best option in my point of view, but I have the 2 little asterisks next to it to say that it's not really happening much. But back in the 1960s, people came up with these reactors called molten salt reactors, and they can essentially use old nuclear waste, like I've mentioned several times. So if we take all of this old nuclear waste that we have all around the world, especially the stuff that's easy to get and high level, that's right there at the power plants anyway, and we install one of these molten salt reactors, we can then use our old waste as nuclear fuel. So really exciting, and I think that's the direction that nuclear is going in from everything that I see. If you want to hear some more stuff about those molten salt reactors, if that piqued your interest, check out some of the videos at the end. We won't have time to watch them probably in class, but check them out. They're pretty cool. So some pictures of what we're talking about. First off, radioactive waste is solid waste. It is not a liquid. It's not a gas. It's not the green slime that you see on The Simpsons. It's solid waste. So you can put it in a steel drum, line that drum with concrete, and essentially seal it inside that drum. Then you can put all these drums either underwater so they can cool off over a long period of time, landfill them, store them underground in whatever way. So solid waste inside of barrels that you store in various ways. Or, like I said, crack them open and reuse the contents. So unfortunately, the way that we're disposing of our nuclear waste is very short-sighted. Most of it today is being stored on-site at the landfills, or sorry, on-site at the nuclear power plants, and then second most is stored at landfills. We're not recycling it, and we're not storing it in deep geological repositories. In fact, there are no operational deep geological repositories as of time of recording this video. In the United States, we got somewhat close. We partially constructed Yucca Mountain, which was proposed in 1987, but due to a lot of setbacks, due to politics, whether that be national or local, whether that be funding, opposition from conservation groups, opposition for First Native people, the not in my backyard sentiment. It has been delayed several times and then finally canceled in 2010, about 15 years ago as of time of recording. Right now, we don't have any long-term storage facility. Like Yucca Mountain was designed to be where we would ship all of our nuclear waste from around the country that we've been building up since the 1950s and to store it in one dedicated location deep underground. This would have been if they did everything properly, safe and totally sealed from the surface. They found one area in the United States that was extremely remote and had very stable geology, so the chance of earthquakes disrupting this facility would have been virtually nil, but it got canceled due to various factors. Right now, Finland has 3 sites that they are constructing. They're the world leader in deep geological repository. None of them are operational, but Onkalo, I hope I'm pronouncing that right, is now saying that it's going to be operational in 2026 as of recording this. So this is what Onkalo looks like, some schematics and then a picture of the construction site, but burying all of this stuff way down deep underground where it can be properly controlled and then properly sealed when it's time to seal it, and then have controlled access points by the government and the military and all that stuff so that it's safe. But that's not really what we're doing. I mean, most of the world isn't using deep geological repositories, but Finland is getting there. So we talked about nuclear waste. Why does nuclear waste have to be stored for so long? That's because of the half-life of some of these radioactive elements. Different isotopes of different radioactive elements are all going to have their own characteristic half-life, the amount of time that it takes for exactly half of that sample to decay. And when I say decay, think undergoing nuclear fission, one parent nucleus, in this case U-238, decaying into its daughter nuclei, in this case the helium, or an alpha particle, but helium, and the thorium. Okay, it's going to take a known amount of time, in the case of U-238, 4.5 billion years, to go from 100% of the sample, or 100% of the sample, down to 50% of the sample. So it's going to take one half-life for half of that sample to decay. Then another half-life, a second half-life, the already 50% is going to decay into 25%, and then 25% is going to decay into 12.5, et cetera, et cetera, et cetera, et cetera. And it's going to take a known number of years or minutes or seconds for each radioactive isotope to undergo its half-life. So again, different radioactive isotopes are going to have different half-lives. All of them are characteristic, all of them are known, and all of them are constant. So we could do some calculations with them. So when we're doing the calculations for half-life, we're going to see them presented in somewhat different ways where we're calculating for different things. I'm not really going to focus on a formula for you guys to memorize. I don't want you guys to use a formula. What I want you to use rather is a process. And if you show this process, you will get credit on the AP test. So the half-life of cesium-137 in this case is 30.2 years. I mean, if the initial mass of the sample is 100 grams, how much will remain after 120.8 years? What I would recommend is that you follow this process. I'm going to list out my knowns. I have the initial mass, I have the half-life because they gave it to me, and I have the amount of time that I'm solving for. What's my unknown? My unknown is the final mass, and that's always going to be in the same unit, whether that is grams, becquerels, percent, as your initial. So what am I going to do? I know that I'm going to go through, I'm going to have to go through several half-lives to get from 30.2 years up to 120.8 years. So I'm going to start dividing between these. 120.8 divided by 30.2 is 4 half-lives. It's very convenient that it works out just that way, and it should pretty much every single time. So I'm just going to start using my mass, and I'm going to take 100 grams and divide it by 2. That's one half-life. I have 50 grams left. After a second half-life, I'm going to have 25 grams. After a third half-life, 12.5 grams. And then after a fourth half-life, because I have 4 half-lives in this problem, I get 6.25 grams. That's how much my final sample is. That's my final answer. Now, if you really wanted to, you could use a formula. You could say the final mass equals the initial mass divided by 2 raised to the number of half-lives, and you can plug and chug and get 6.25 grams, and you see that they're the same. That formula isn't so bad, but let's look at another problem. So for the second problem, we have an archaeological dig in Scotland, and they get a mummified bog body in a Scottish peat bog where the soil is so acidic and so anoxic that bodies don't dissolve. Carbon is stored in peat bogs. Anyway, I get off track. If the half-life of carbon-14 is 5,730 years, how old is the sample if 12.5% of the original carbon in this body remains? This is how they do carbon dating. So if any of you guys have looked at an archaeological episode and have like any type of carbon dating, this is how they do it. We know the half-life of carbon-14. So what's our initial sample? Our initial sample is 100%. They don't give you that really, but we know that we have to go from 12.5%, so we need a percent. So we know that our starting percentage when this person died was 100% of the starting amount of carbon-14 would have been in their body. We're given the final percent, we're given our half-life. So our unknown in this example is time. How long will it take? So we're just going to go through this until we get from 100% down to 12.5%. 100% divided by 2 is 50%, divided by 2 is 25%, and then divided by 2 is 12.5%. This is 1, 2, 3 half-lives. So I know that this is 3 half-lives. I multiply 5,730 years by 3 half-lives, and I get 17,200 years. I use 3 half-lives because that's what I got up above. Now, this is where I would stop using the formula. If I use this second formula, my final mass equals my initial mass over 2 raised to the power of t divided by t1 t divided by your half-life. I don't want to have to solve for an exponent in the denominator of a problem. It just sounds like a pain. So I'm just going to use this process, and I'm going to get 17,200 years. So we've worked through 2 together. So what I want you guys to do for this problem is pause it and then work through this problem on your own. Okay, now that you're hopefully back, after 200 million years, only 1/16 of the original sample of a particular radioactive waste will remain. The half-life of this radioactive waste is how many million years? Yes, I know this isn't as specific as the last examples, but let's go through it. We know that our original amount was 1, same as the last one with 100%. Our final fraction is 1/16, and our time is 200,000 years. We would just go through this. 1 divided by 2 gives us 1/2. 1/2 divided by 2 is 1/4, then 1/8, then 1/16. So I got 1, 2, 3, 4 half-lives in this problem. And then I know my final amount of time. I know t, that's 200 million years. Divide that by 4, and I get 50 million years as my half-life. Some of you guys maybe even looked at this problem and did it in your head, especially when you wrote out 200 million, or sorry, 200 million like on paper. So 50 million years. All right, and the last thing that we need to talk about is nuclear disasters and the safety around nuclear power plants. So we're going to be talking about three disasters, Chernobyl, Fukushima Daiichi, and 3 Mile Island. These actually don't represent the three biggest disasters. Chernobyl and Fukushima Daiichi do represent the first two, but 3 Mile Island is pretty far down there. We're not going to be talking about some of the minor stuff. We're not going to be talking about some of the stuff that's more local to us in Colorado, like Rocky Flats. We're not going to be talking about nuclear weapons testing or nuclear weapons use. We're just going to be talking about nuclear power plants. So the first of these three accidents that we're going to have to talk about is 3 Mile Island. And for 3 Mile Island, you should know generally what happened, but not in a ton of detail. Just know where it occurred and generally what happened. Now let me set the stage for you with nuclear power first. Nuclear power came out of nuclear weapons. So World War II, the US and then Nazi Germany were in an arms race trying to develop nuclear weapons, and the Manhattan Project in the United States got there first, originally as a deterrent to the Nazis and Germany, but the war ended before they were used in Europe, and then they were uh, relatively quickly afterwards used in Japan at Nagasaki and Hiroshima. And there was always in public, then people saw all the horrible stuff that came out of those two cities with the after effects like radiation sickness and everything else, and the devastation from the nuclear weapons. So public perception of nuclear power was always plagued or always shadowed by nuclear weapons because they came out of nuclear weapons. The weapons were designed first, and then the power plants were designed second, and they were always in the scientist's mind, but it was a wartime effort, and they were focused on making the weapon first. So, in the post-World War II era, the 1950s, 1960s, the atomic age, we have the widespread adoption of nuclear power in the United States and worldwide, especially in Europe. And nuclear power quickly became a dominant force of, well, not dominant, but a relatively large force in the power generation sector. People saw it as a clean, reliable, consistent energy source, which it absolutely is, especially communities that were former coal burning power plants were shut down, and then a nuclear power plant opened up in the same community. And you go from all this atmospheric pollution, especially the particulate matter of the coal, to nuclear, and people saw the difference. But it was always shadowed by nuclear weapons. So into the 1970s, 1978, public perception wasn't great. 1979, public perception wasn't great as we moved into the spring of 79. It was coming out of the environmental movement, hippie movement, and the post Vietnam War movement or period. So public perception for nuclear wasn't great. And then we have this accident in the United States where we have this nuclear power plant that had a small partial meltdown inside of the radioactive core, but there was a containment structure around it. So that containment structure worked, it did its job, and we only had a small amount of ionizing radiation that got into the atmosphere and into the water of the Susquehanna River, where this power plant was located. The main cause of this, there was definitely human error. There was some negligence. There was definitely poor training. But one of the mechanical things was that a flashing red light that should have flashed when there was a problem didn't. So, there was definitely some equipment error as well. But nobody died in this. There were only voluntary evacuations, and no deaths from the accident have ever occurred. And many studies have shown that there was no long-term effects for people or the environment of the area. But this definitely slowed down nuclear power industry in the United States. Essentially, we really slowed down the construction of new nuclear power plants after 3 Mile Island. So just some pictures of the plant itself, some protests afterwards, and the cleanup afterwards. And then there was Chernobyl just a few years later, about 7 years later, public perception of nuclear really tanked worldwide, and that was because of Chernobyl. So this is definitely the worst nuclear disaster in history. You guys should know that it occurred in modern Ukraine, which was formerly the part of the USSR. Um, Essentially, what they were doing was a routine safety check, and the crew that was supposed to work this safety check was the day shift. They were trained for it, but then they were told that they couldn't do the drill during the day. They ended up doing it at night instead, and the night crew had no idea that it was even happening. They weren't trained for it, and they came into work that day saying like, "Here, do this," and they had no idea what they were doing. They were supposed to shut down the reactor, but instead of it and then just reboot it back up, shut down the reactor and then make sure that it could stay cooled from some residual circulation of the cooling fluid, and then just bring it back up using that as the energy source. But instead of it shutting down, they had an uncontrolled chain reaction that occurred instead, and massive amount of energy released in a short amount of time exploded. This was followed by a nuclear core fire, like an open air nuclear fire. They didn't have a containment building, so this debris rained down from where the core was all around the surrounding area, the different roofs of the structure nearby. So this is an example of it after, or this is a picture of it rather, from a helicopter after it had exploded, and then as they were trying to do the cleanup efforts. So you can see how difficult this would be to clean up if there was no containment building around it. They didn't have a containment building because it cost too much, so they weren't able to contain this accident in that building. Tons of ionizing radiation went to the atmosphere. The USSR initially pretended as though everything was all right. They didn't notify the public. They didn't have any evacuation zones until it was located international, like detected internationally, first in Scandinavia. So then they had an evacuation zone that was relatively small, and then they widened that evacuation zone and then widened it again. Eventually, a 30-kilometer evacuation zone of about 1/3 of a million people from around the plant. The initial cleanup took months, and at least 500 personnel were estimated to have been in that cleanup effort, and that cleanup effort cost around $35 billion in the U.S. currency, U.S. dollars. There was, the year that it happened, a sarcophagus, so a structure built over this. You'll see a picture of it in a second. And then that was only supposed to be like a temporary fix, and it wasn't until 2017 that the Chernobyl New Safe Confinement structure, which was the biggest mobile structure ever. There's a really cool documentary that I can point you towards talking about how it was constructed, and then moved this giant building, like this giant football stadium dome, was moved over the power plant. So super cool. Um, there was officially, according to the USSR, only 30 deaths, although virtually everybody contests that number, including locals who lost family members. The Russian Federation never updated that number, but it's difficult to determine the long-term incidence of cancers, birth defects, all of those things that happened in people that were affected by the radiation in the city of Pripyat in Ukraine. So anything from 4,000 to 60,000 individuals that are, you know, could have potentially died from this or the resulting cancers over the decades. So where this occurred, northern Ukraine, modern day Ukraine, formerly part of the USSR, and again that ionizing radiation got blown up into the atmosphere and then drifted on the prevailing wind currents and detected in Scandinavian countries first. I might be mistaken about that, but anyway, uh, detected internationally, and then then the USSR owned up to it. The cleanup efforts, super crazy. You can see the devastation on this roof that these people had to clean. These guys were sent out in shifts of like 30 seconds or a minute wearing lead aprons and like totally head to toe covered in lead to protect them from the radiation. Then they can shovel for like a minute or half a minute and then their shift was done and they were called off, and then that was their total radiation dose. They couldn't be allowed to do anything else in the cleanup efforts. They were just sent home after that. So massive cleanup effort. The documentary HBO's miniseries Chernobyl, if you want to explore this in more detail, is really, really good. I'd highly recommend it. And then the picture on the bottom right of the previous slide was the Chernobyl new safe confinement structure, that largest mobile structure ever. The last disaster that we need to talk about is Fukushima Daiichi. This occurred in Japan after a 9.0 earthquake in 2011. When Japan was in terms of their nuclear power, they thought that they were really prepared for the effects of a tsunami. But this was a massive earthquake. 9.0 is the second or third largest ever detected on record since records began. And they massively underestimated the size of the tsunami that was gonna reach them. So essentially, what happened was that the plant automatically shut down once they got the detection of the offshore earthquake because they knew that there was going to be a tsunami. The diesel generators should have kicked in, and those diesel generators are supposed to continue circulate cooling water around the nuclear core. If you shut down the power plant, you want to still have some power in order to keep that cooling fluid moving, because if you don't, then the reactor is going to overheat, you're going to have a chain reaction, and it's going to end up exploding. But the tsunami breached the tsunami that was 14 meters, breached the 6-meter seawall that was protecting the plant. And unfortunately, whoever designed this plant put the diesel generators in the basement. So they flooded, they shut off, and that shut off the cooling water that was supposed to be circulating around the nuclear core. The tsunami flooded reactors 1 through 4, and we had nuclear meltdowns in units 1, 2, and 3, and then a partial meltdown in unit 4. There was explosions in cooling ponds as well, because the nuclear waste has to be continually circulating water around it, and that stopped as well, so you had some explosions in the cooling ponds. But those reactors had containment buildings, and that contained much of the atmospheric radiation, or radiation that would have gone into the air, but it didn't do anything to contain the radiation that went out into the ocean. There was an evacuation zone of 20 kilometers radius, and 154,000 residents were evacuated. A lot of material did end up going into the atmosphere, but more ended up going into the ocean and washed out into the Pacific. The radiation levels were detected all the way from Washington State, California, Central America, South America, like Peru and Chile. There was estimated to be 30 to 40 years to complete the cleanup operation, and it's going to cost tens of billions of dollars. But there were no deaths from Fukushima. Nobody died of radiation sickness. Nobody died of the immediate effect of the plant of the meltdowns. You can contrast that with the tsunami that did kill, let's say, 18,000 people. So the tsunami was absolutely devastating. Fukushima Daiichi was really bad. It shouldn't have occurred, and it has definitely had impacts on Japan's nuclear perception, but it didn't kill anybody. So the Richter scale 9.0 is the third largest earthquake in history. So massive, massive, massive earthquake. And we got some pictures of it. So units 1 through 4 are in this structure down here. You notice units 5 and 6. I didn't even mention those on the previous slide because they weren't impacted. You can see the radiation that spread throughout the Pacific Basin, the Pacific Ocean Basin. So radiation levels detected all around the Pacific Ocean. That is definitely bad, but it could have been a lot worse. And then some of the cleanup efforts, fighting the fires, etc. So those 3 disasters have really impacted perception of nuclear energy worldwide. But despite those disasters, nuclear is still rated one of the safest in terms of deaths per terawatt hour. This is even factoring in the higher end estimates of deaths from Chernobyl. We have generated lots and lots and lots of electricity through nuclear worldwide. This is measured in terawatt hours. So if we're looking at death rates per terawatt hour, we've generated a ton of electricity, and that death toll is only to 0.07 deaths per terawatt hour. So um, it's been working operationally in thousands of plants, maybe hundreds of plants worldwide, and we only have to talk about three accidents, three that really shook the industry. Um, I do want to point out again that there are no CO2 emissions. There are no other greenhouse gas emissions besides water vapor. And water vapor is going to precipitate out of the atmosphere anyway, and it's going to go through the short-term water cycle of evaporation and condensation anyway. Um, the there like that can't be stressed enough. And when we're talking about clean energy sources that have relatively low environmental impacts, nuclear is the highest, if like I would argue the highest. Um, so unlike solar and wind that have very short lifespans of those solar panels and wind turbines, a nuclear facility will last a really, really long time. If we can reuse those that nuclear waste, we get rid of the waste issue, or at least a large portion of the waste issue, and we don't create any atmospheric pollutants at all. So I would say that in an ideal scenario, if I was to choose my energy sources in terms of safety, both human health and environmental, versus the environmental impact, I would go for nuclear with solar and wind being the variable energy sources that I combine with it. Notice that I did not put a star, what my poor attempt of a star is, next to hydroelectric. I would go nuclear. But there are people that will argue otherwise, and we have to look at some of the economics behind this. So where do we have the uranium? Highest reserves are in Australia, and then you see some reserves in Asia, the Americas, and very little in Europe, Africa, and the Middle East. So we have to consider where we can mine this uranium from and what type of access we have in the global markets. That is to say, we may not see nuclear power plants where we don't have the uranium or the capital to ship in the uranium. Um, so look at some of the countries like all of Africa except for South Africa, and some of South America that don't have nuclear power. But then we got some oddities, like some countries in Central Asia that have access to the uranium, Australia being a notable question mark, what's going on there. But in terms of share of nuclear energy, France has been doing safe nuclear for decades, and they get 3/4 of the electricity from nuclear. They're the world leader in nuclear power, and France should be a model for what other countries can do. Some countries have greatly decreased their amount of nuclear. Germany, for example, Japan, for example, greatly reduced the amount of nuclear that they were using after Fukushima Daiichi. Both countries started shutting down nuclear power plants in direct response to the disaster. And then Germany is shifting towards solar. Why would Germany, a northern European country with few daylight hours in the winter and cloudy skies most of the rest of the year, shift to solar? The cynic in me is that it's public perception and it's greenwashing and it's what looks good. But nuclear power is declining in Germany. It's stagnant in the United States. We can talk about this all day long, but what I want you guys to know is those three countries, or four countries rather, highest proportion in France, decreasing in Japan and Germany, and then stagnant in the United States. And when I say stagnant or decreasing, I really mean it. So if we look at the time of those disasters, we see a small, like look at the growth model, like both the line, which is the operable capacity, and the bars, which is the number of reactors that we have in operation. 1979, there was a slight pause, right, after 3 Mile Island, but the U.S., yeah, we had a bit of a slight pause, but we continue to build them. Worldwide, they continue to get built until 1989. This solid bar right here, like the different colored red bar, Chernobyl. and then basically plateaus. Global response is to not approve really any new nuclear reactors. I mean, not like new nuclear reactors got built. Obviously, they did. Some got shut down, some got built. Some countries continue to build them while others were shutting them down, all of that stuff. But worldwide, they plateaued through the 1990s, 2000s, and then after Fukushima Daiichi, they even started to decline in number of reactors that were open and operational. Okay, so like I said, notably, Germany and Japan were both phasing out their reactors in direct response to Fukushima Daiichi, although it is starting to look like Japan's going to backtrack on that a little bit, just because of economics, right? They need nuclear power. All right, so if you're interested in exploring nuclear a little bit more, check out these other videos, molten salt reactors, why we shouldn't just rely on variable renewable energy resources, and why we need nuclear power. So the learning objectives, uranium-235 is a fissile material and it undergoes radioactive decay, releases a lot of energy to power our nuclear power plants. And that's what the majority of our power plants are on, and that's the one that we described how it works. We talked about radioactivity. We talked about how U-235 remains radioactive for a really long time, and that's going to create nuclear wastes. And those wastes have to be disposed of. And nuclear is a non-renewable energy source, but it is clean compared to the fossil fuels. We talked about the disasters and how to calculate half-life. So hope you guys learned a lot, and I'll see you all in class. Bye.